Recording should happen any second now. Alrighty, and there we go. Great, so we can go ahead and get started. So just a couple quick announcements, and then we will get into the discussion and talking about the actual algebra that we started just learning about with the most recent lecture. So first couple things, office hours. Hopefully all of you should have received the invitation or the meeting notification that it's been created. Office hours are set to begin this Wednesday. I know that I said office hours are Monday and Wednesday. Unfortunately, I can't meet today. I do have a prior engagement, so office hours will begin Wednesday, 4:15 to 5:15, and then every week moving forward, it'll be Monday and Wednesday, 4:15 to 5:15. If you're busy Wednesday and you wanted to meet with me and you were expecting to be able to do it today, just let me know. We can, set up a private meeting and we'll just figure out a different time that, works for both of us. Okay. So just get in touch with me and let me know. Second thing here, just as a reminder, I know I've had a couple slight roster adjustments. So just to the new people, you do not need to send me your homework. Okay, so homework not graded, not collected. The only time you ever need to send me your homework is if you're experiencing a difficulty with, a particular question and you want to show me as far as you've gotten, or maybe you want to, just show me and ask me, hey, is this right? It could be that simple. That's totally fine, right? You can definitely do that. But as far as collection, you do not need to do that. Did you send the office hours notification as a team meeting? Yes. We're meeting in Microsoft Teams for our office hours. So it should be a separate team meeting labeled as Mat 104 office hours. Hopefully that answered your question. But again, back to the homework thing, you do not need to send me your homework unless you actually have a problem with the homework, in which case, absolutely fine. Okay? Okay, and last final reminder, please make sure that you understand how to use OneDrive and how to submit your work through OneDrive. Your first quiz will be this Friday. And the expectation is that you're going to take the quiz and you're going to send me your work through OneDrive. So if you still don't, if you're not having an easy time with it, if you don't really know what to do with it just yet, please contact me, reach out, and I will try to help you as best as I can. Okay, so OneDrive, very important. Okay, so that's all I had for announcements. So yeah, let's go ahead and discuss the most recent lecture. So in this recent lecture, we kind of started covering fractions as far as how we handle complex fractions and turning them into simple fractions. We discussed unions and intersection as far as sets are concerned. So we dabbled a little bit more with sets. And we also talked about exponents and the different rules regarding exponents. So let's tackle first union and intersection regarding sets. So first off, let me put an example here. Let's say we have two sets here. So we have set A, and in set A, we have the following elements. Remember, a set is just a composition of a bunch of things, right? Things that are inside of it. Generally speaking, for us, for our purposes, it's just going to be numbers, integers, right? But it could also house variables and other unknowns. So here we have set A, and in set A, we're going to have -2, -1, 0, 1, and 2. And then for set B, we'll have the following. We'll have -2, 0, and 2. Okay, so if I were to ask right now to find the intersection and the union of these two sets, how would I proceed to do that? So again, let me write this down. We have this and this. And just for the sake of clarity here, of the two, which one is the intersection and which one is the union? So of these two right here. Helen?
The top is intersection and the bottom one is union.
Yep, the top one. So the top one reads A intersect B, and the bottom one reads A union with B, or A union B. Perfect, thank you. Okay, so what we want to do here is let's take it one at a time, right? Let's do, even though I wrote intersect first, let's do the union one first, right? So let me scroll up so I can actually show what's going on here. So I want to do A union with B first. Now, how do I do this? What is union? What does it mean if I have two sets being unioned together? In your own words, totally fine. Abigail?
You're combining both sets together.
Yeah, we're taking two different sets and we're kind of merging them together, right? And what happens if we have an element that's in both sets, Abby? So for example, I have -2 and -2, right? So what happens with -2?
You just write it once because you don't have to write it twice since it's, or you're talking about the the union.
Yep, you got it perfectly right. So, and that's just it, right? So what we're going to do here is we're going to look through all of the elements that are in set A and all of the elements that are in set B. And what we're going to do is we're going to write them all down. And if there's any duplicates, well, we can throw those out, right? We only need to write it one time. So the set A union B, what we're going to do, again, we're going to write down everything that we have, right? So in set A, we have -2, -1, 0, 1, and 2, right? So we can start writing that -1, or I'm sorry, -2, -1, 0, 1, and 2, right? Okay, and in set B, we have -2, 0, and 2. But notice that we already have those, right? We have -2, 0, and 2. So set B, even though we're unioning it with set A, I'm not sure that's a verb, but I'm going to use it as a verb here. We see that everything that's in set B, all of its elements are all duplicates, right? So we don't need to write it a second time. And in fact, what we can see here is we actually just ended up with set A again, right? So A union with B really just gives us, this is still just set A, right? It's the same thing. We could go and take this a step further. We talked just a little bit about sets and subsets and what it means for something to be a subset. This was back in the first lecture. We can say that set B is in fact a subset of set A because all of the elements that are found in set B are also found in set A. But the opposite is not true, right? We see that set A has -1 and also 1, and set B does not have that, so A would not be a subset of B. Everybody with me so far? Any questions on that? Okay, great. So let's, sorry, Matt, do you have a question?
Yeah, so a subset is when the numbers are present in both A and B.
So a subset is when you have the numbers present in both. That's correct. It needs to be in both, but one of the sets is not going to have everything that the other set does, right? So we see that set B has all of the set A has all the elements that set B does, right? Set A has -2, has 0, it has 2, just the same that set B does as well, right? But notice that B is a smaller set. It doesn't have -1, and it also doesn't have 1. So as a result, B is a subset of A. Does that make sense?
Yeah, thank you.
Yep. Good question. Anything else on this before we move on? All right, let's take a look at the next one. So next one, what we want to do is we want to look at the intersection between the two sets. So A intersect with B. How do I do this one? What is A intersect B going to look like here? Any takers? Okay, so Denny, you have an ID here, right? Denny says that the intersection of A and B should be -2, 0, 1, and 2. That's almost correct, right? We're getting there. But what could we do a little bit? What's the only number in there that we can leave out? Vincent?
You leave out the 1.
We leave out the 1, right? And why do we leave out the 1, Vincent?
Because you're only listing the elements that are in both sets.
Perfect, right? So the intersection operation, what that's telling us to look for is the elements that are in only the elements that are listed in both, right? So if we're looking at these elements, we can kind of like do some matching, right? We see -2 is here, -2 is here. Perfect, okay? We take a look at the next one that's found in B, right? So the next one found in B is 0. So we have a 0 here, great. We also have a 0 here. And then lastly, we have a 2 here, and we also have a 2 here, right? So when we list these elements for this intersection, we're only listing the things that both sets have in common, right? So this is just going to be -2, sorry, pen stopped working momentarily, -2, 0, and 2, right? And as far as the -1 and the 1 are concerned in set A, well, we omit those because of the fact that it's not present in both sets. Again, just like Vincent mentioned, we're only looking for the things that are found in both. So because -1 and 1 are only found in set A and not found in set B, it would not be in the intersection of the two. Again, the way that I said it in the lecture is you want to, when you see the intersection operation, you want to think of like a Venn diagram, right? So excuse my very crude drawing here. Venn diagram, what you're doing is you're looking for the stuff that's in common, right? That's where intersection lives. You're looking for the elements that are between set A and set B, or whatever the sets may be in that case. Okay, any questions on this before we move forward? Okay, great. Let's go ahead and move on to the next one. So I want to do one more example of union and intersection, only because in the lecture, I only spoke about sets. And in the homework, there was a question regarding union and intersection that had to do with intervals. That was on purpose. I wanted to kind of give you a little bit stranger of a question here. But you know, let's take a look at an example regarding union and intersections of intervals, and either that will verify your work or maybe you still have a question on the homework, okay? So let's say we have the following. Let's say A and B this time are intervals, okay? So we have A and we have B. So A here is going to be the interval from -4 to 2. B is going to be the interval from 0 to 5. And quick, I'm going to call on somebody at random here. Let's see. Ella, please tell me, what do the brackets mean? Notice that they're brackets, not parentheses. Okay. Somebody else help me out. What does the bracket mean as far as intervals are concerned? That there is a solution? Not quite. Xavier?
Doesn't it mean that the numbers are included in the solution?
Yes, exactly. So what it means is that the endpoints are going to be included in the intervals, right? If, for example, we saw, just hypothetically, if we had this instead, -4 to 2, I promise that's a 2, there we go, then what this would mean is that the endpoints are not included in this interval. All the other numbers between them would be, but specifically not the endpoints. That's what you meant? Yeah, sorry, that's not what I gathered from your answer. But if that's what you meant, then perfect, Denny. Okay, so again, we have the following two intervals. A is from -4 to 2, endpoints included. B is from 0 to 5, also endpoints are included, right? So what I want to do is I want to figure out the union and the intersection of these two intervals. So again, we're going to write. Let's do the union first. So we have A union with B, and then we also have A intersect with B, right? And I want to figure these two things out. So it can be very helpful, especially when we are dealing with intervals, to list them out or graph them on the number line, right? So what I'm going to do is, just for the sake of keeping things nice and orderly, I will graph both of these on the number line just to see exactly what we're looking at. Set A, I will go ahead and notate in red. Set B, or interval B, I will go ahead and notate in blue, okay? So let me go ahead and draw this really quickly. So we see that the furthest left that any of this goes is -4. So I will plot -4 over here. We know that this at some point crosses 0. And let's go ahead and put 2 over here and 5 over here, right? And of course, this goes off to infinity. in either direction, infinity and negative infinity. Okay, so graphing from -4 to 2. Let's go ahead and graph set A. What's this going to look like? Well, obviously, we are talking about this specific interval here from -4 up until 2. And again, quick question. What kind of circles or dots am I using? Closed or open, based on the fact that I have brackets? Kendra.
Would it be closed?
It would be closed. You would be correct. Perfect. So we want to use closed dots on -4 and on 2 because of the fact that we are including those endpoints. Remember, if they were parentheses, then we would not include those endpoints, just like we had just discussed, and then we would be using open circles or open dots. Okay, so we have this set in red, and that's of course going to notate interval A or set A here. Okay, and now to do B, we're talking about from 0 to 5, right? So 0 to 5, and just to keep things nice and clean, I'm going to put the blue underneath the red so we don't have too much color overlap here, making it a terrible mess. Again, notice we're going to use closed circles here or closed dots because of the fact that we are including the endpoints. So closed circle, closed dots on 0 and 5. Okay. So now what we want to do is we want to figure out the first thing, which is A union with B. Again, think about what union means. Union means we're taking all of the things that are present in the first set and all of the things that are present in the second set, and we're just pushing them together, right, to make one larger set. We're combining them. And any duplicates, well, that's okay if we have duplicates, but we just throw them out, right? We don't need to list everything twice. So where are we going to start then for A union B? What's going to be the furthest most left element that is included in our set? Anybody have an idea? -4, yes, Gianna, exactly. So we are starting from -4. So we are going to have -4, and keep in mind, we're going to be using a bracket here because, of course, the endpoint was included. Ah, my pen is dying. This is terrible. What a travesty. Okay, so we're starting from -4. And now we're going to continue on moving down the number line to the right here until we no longer have an element that we're counting, right? So notice that everything in red we're counting, right? And there's this brief overlap of red and blue, and that's happening from 0 to 2, right? This is where you would generally see, if we were talking about sets, this is where we would see the duplicates, right? In the previous example, we had -2 was a duplicate, 0 was a duplicate, and 2 was the duplicate, right? So all of those things were duplicates. So as a result, we only needed to list it twice. Or I'm sorry, we only needed to list it once. So here we see that there's some duplicates going on, but that's okay. We just know that the area from 0 to 2 is included because even though it's in both sets, as long as it's in just one set, it would be included in the union, right? So we can just keep on moving right along past that area and notice how it's going from -4 and it's stretching all the way across up until we get to 5, right? So we get to 5 and that's where we stop. And we're putting a bracket because we're including the value 5, right? So our new set here, A union with B, is really the total collection from the furthest leftmost element on the number line all the way up until the furthest rightmost element on the number line. So in this case, it's just taking into account from -4 to 5 and all the values that are included in between. If you recall, when we were discussing intervals the first time, we kind of talked about how this doesn't just mean -4, this doesn't just mean 5, it means all the values in between as well. And that's really what we accomplished here, right? Okay, so with that in mind, let's now think about the intersection. So intersection, again, think Venn diagram. Think of only the stuff that's in common, right? So with that in mind, who thinks they have the answer to this? Dylan?
Is it just 0 and 2?
Yeah, it's the area, or the interval from 0 to 2. And now what I want to notice is that keep in mind, because 0 and 2 are found in both sets, what we can do is we can include it. So we're going to have, again, brackets here, the interval from 0 to 2 with the endpoints included. Perfect. Does anybody have any questions on this? Okay, Great. So let's go ahead and move on from union intersection. Oh, I'm sorry, Abby, do you have a question?
Yeah, I was just wondering if you could explain why we included 0 again.
So we're including 0 because of the fact that 0 is found in set B, right? So sorry, let me use a different color here. So notice how 0 is being included in set B because of the bracket. Well, 0 is also included in set A as well, right? If we're talking about all the numbers between -4 and 2, 0 is definitely in that range, right? So if 0 is included in A and 0 is also included in B, then it should be included in the intersection of A and B, right? If it's in common, then we take it. So as a result, 0 would be included. For the same reason, 2 is also going to be included, right? Because notice how we have a bracket for 2 for set A, which means we're including that value in set A. And 2 is definitely in between 0 and 5, right? So it's definitely in set B as well. And so as a result, we would put a bracket for 2 in the intersection of A to B. Did that answer your question?
Yeah, thank you.
Yep. And that's actually a really good question because we should, before we move on, let me just slightly change this question, right? If, for example, just hypothetically, if set A were instead from -4 to 2 with a parentheses on 2, this would not necessarily work the same. Why would it not work the same? Well, because 2 would no longer be included in set A, right? That's what this parentheses means. It means that the endpoint is not included. So as a result, if it's not included in A, even if it's included in B, it would not be included in the intersection. So we would have to change this to be from 0 to 2, where 0 is included, but 2 is not. So that's a great point by Abby. Okay. Any questions? Any other questions before we move forward? Okay, great. So let me go ahead and clear my screen here, and we'll move on to the next thing. So we talked about fractions in this lecture. This was, we even talked about it in the last meeting a little bit, but we kind of looked over a more formal policy on how we deal with complex fractions. So best way, again, to just get into it is just with an example. So let's say I have this complex fraction. We have 1/5 being divided by 9/2. What was the acronym that we learned in the last lecture, or possibly from math classes prior? What are those 3 little letters that we need to remember? I'll give you a hint. It always reminds me of chicken when I hear it, even though the letters are slightly, flipped.
Keep, change, flip.
Yeah. Yep. Keep, change, flip, KCF, right? That's exactly what we need to remember here. So whenever we're dealing with a complex fraction, which by definition is just fractions within fractions, right? If you think of the movie Inception, it's that, but way less exciting. So we're dealing with 1/5, which is a fraction, being divided by 9/2, right? So we have 2 fractions, and then there is this larger fraction going on. So what we do, the way that we handle it is we use the practice keep, change, flip, KCF. Okay, so somebody help me out. What does this necessarily equate to? What does keep refer to? What am I keeping?
The numerator?
Numerator, yeah. So what this means is we're going to keep 1/5 the same, right? So we're just keeping 1/5 as 1/5. Perfect. Okay, let me call on somebody here. Jacqueline, help me out. What am I going to change then? So the C in keep, change, flip.
I'm sorry, can you repeat that again? You cut out on my end.
Sure, I was asking you with the acronym KCF, right? Keep, change, flip. What am I changing?
I think it's the numerator.
Okay, so remember that the K is referring to the numerator, right? We're keeping the numerator the same, so 1/5 is just going to stay as 1/5. Can anybody help her out? Anybody remember what we're changing? The denominator? Not quite. we're not there yet, right? So there's something we have to do first. We have to do something before we deal with the denominator, right? So remember that the k deals with the numerator, the f deals with the denominator, and we have to, deal with those separately. But there's one thing we have to do first. Dylan?
Is it the sign? Would you multiply them?
Yeah, exactly. So right now, the two, what's going on, the relationship between 1/5 and 9/2 is it's being divided, right? 1/5 is being divided by 9/2. So what we're going to do, the thing that we're changing is we're going to change that division into multiplication. So now the operation is changing from division to multiplication, and now we can move forward to the next thing. Jenna, do you have a question, or were you just trying to answer?
Oh, I was just going to answer.
Okay, sure. So now, and somebody actually already mentioned the next thing that we have to do, right? So keep refers to the numerator, we keep it the same. Change refers to the operation, so it's from division, we change it to multiplication. And flip, well, the flip refers to the denominator. So instead of it being 9/2, what we do now is we flip it to be 2/9 or 2/9. And that's it. That's how we handle this complex fraction. Keep, change, flip, and now we can go ahead and proceed. Okay, so with fraction multiplication, how do we do this? Fraction addition, subtraction is a different process. With multiplication, it's pretty straightforward, right? We just multiply straight across. So we multiply the numerators, and then we multiply the denominators, and we end up with just one fraction as a result, right? So multiplying the numerators, we have 1 times 2. This, of course, gives us 2. And multiplying the denominators, this is 5 times 9, which is 45. And that's it. That's our final answer. We leave it like this. Please, and again, I know I had a couple of roster changes, so if you're new to this class, do not give me the decimal. Decimals are gross. They are super annoying to manage. Leave it like this. This is totally fine, right? We took a complex fraction and we reduced it to a simple fraction. So 1/5 being divided by 9/2 gives you the answer 2/45, or 2/45. Okay? Anybody have a question with the process that we did here? Okay, let's go ahead and move on to our next fraction example. So let's get a little bit more challenging here. Let's say we have 2/3 being divided by 1/4 plus 1/5. So notice that we still have a complex fraction, right? There's still a decent amount going on here. We have, 2/3 is a fraction, 1/4 is a fraction, 1/5 is a fraction. And then there's, of course, the larger fraction going on, which again, by definition, makes this a complex fraction. So what I want to do is I want to make this into a simple fraction. Okay, so what's my first step if I'm dealing with this? We can't immediately go to keep, change, flip just yet, right? Because keep, change, flip kind of requires it to be in the form of one fraction over another. For this, notice that we have this addition going on in the denominator. So we have to take care of that first. So how do I add 1/4 and 1/5? What's my process going to be here? Carolina?
Get common denominators for both.
Common denominators for both. Perfect. Okay, so what we're going to do here is we want to look and find the common denominator between 4 and 5. What would you recommend, Carolina, since you just answered?
20.
20, perfect. Okay, so what we're going to do here is we're going to multiply each of these fractions cleverly by 1, right? We're not going to change the value of the fraction. We're just going to change the fraction's appearances. So we are going to deal with 1/4 first. So if I want to get this 4 to be a 20, what I have to do is I have to multiply it by 5, right? To get 4 to equal 20, we multiply it by 5. Great. And now what I also have to do is remember whatever we do to the bottom, we also have to do to the top, right? So since I multiplied the denominator, the 4, by 5, I also have to multiply the numerator, or the 1, also by 5. Okay, and what we're going to do is we're also going to repeat this process for this other fraction, but instead of multiplying by 5/5, we're going to multiply by 4/4. Again, the goal here is we want to get 20 in each of the denominators. So that's exactly what we're going to do here. Okay, so rewriting everything, we end up with 2/3 on top. We haven't touched that yet. And we end up with 5/20, or 5/20, plus 4/20, right? Again, 5 times 1 gives us 5 in the numerator, 5 times 4 gives us 20, and then 4 times 1 gives us 4 in the numerator, and 4 times 5 also gives us 20 in the denominator again. So now that we have common denominators, we can do this fraction addition that's happening in this larger denominator, right? So we have 5/20 plus 4/20. So as a result, because they have the same denominator, we know that this should be equivalent to, again, 2/3 isn't changing. This is the same thing as keeping our denominator the same, so it's still over 20, and we just do the operation in the numerator, right? So 5 plus 4 happening in the numerator gives us a 9. Okay, so now we have 2/3 over 9/20. Well, now this is looking much more reasonable and much more applicable for KCF than before, right? We couldn't use KCF here because the addition in the denominator would mess us up, right? But now that we only have just this one fraction in the denominator, we can apply it. So using what we just learned, somebody help me out. I want to use KCF here. Take me home with this. So what's my first step? Jenna.
You're gonna keep 2/3.
Great. So we keep 2/3. What's going to be the change?
The sign, so it's gonna be multiplication.
Perfect. And what's the flip?
It's gonna be 20 over 9.
20 over 9. We take the bottom fraction instead of 9/20, we flip it to be 20/9. Perfect. Okay. So great. Jenna got us more than halfway there. Now somebody help me out. Somebody else. I want to do fraction multiplication. How do we do this? Anybody, I promise I will not bite. Carolina?
Oh. Straight across, 40 over 27.
Yeah, we multiply straight across, right? So fraction multiplication just means you multiply numerators and you multiply denominators. So in the numerator, 2 times 20 gives us 40. In the denominator, 3 times 9 gives us 27. And this is your final answer. So once again, we have taken a complex fraction, 2/3 being divided by 1/4 plus 1/5 in the denominator. And through various processes, changing to get common denominators, and then doing the fraction addition, then using KCF, we end up with a simple fraction, 40/27. And again, this is a good place to stop it. Okay? Any questions with the procedures that we use for fractions here? Okay, great. So let's go ahead and move on from fractions. So the last major topic, I know we discussed absolute values in the lecture, but I'm not too focused on absolute value just yet. That'll make a resurgence later on. The last big topic that we talked about in the most recent lecture were exponents. So let me pose a question to the class. What, in your own words, it's fine, what will a negative exponent do? What does a negative exponent do to the base that it's on? So let me actually just give an example so that way we can see. If I had 3 to the negative 1, what does this do here? Helen?
It makes it less than 1.
So for the record, just try to use the hand raise feature so that way I can call on you guys individually. But I appreciate whoever just spoke up. But Helen, do you want to give that a shot again? I didn't hear you.
It makes it less than 1.
Makes it less than 1. Okay, so that will be true for whole numbers or for integers when there's a negative exponent attached to the base, but not necessarily true if we had, for example, this, right? If we had a fraction raised to a negative power, then that wouldn't necessarily be true that it's making it less than 1, right? So just for the case that I have here, 3 to the negative first power, you're definitely half right that it makes it less than 1. But what is it actually doing? Well, it's taking our base here and it's just flipping it over, right? Currently, right now, this is 3, or another way we can write it is 3 over 1, right? So what we can do is the negative exponent says, okay, just go ahead, flip it over. So this is going to be, instead of 3 over 1, this is now going to be 1 over 3. And whatever the exponent was, just now make it positive, right? So 3 to the first power, which of course we know is just 3, right? So this is just 1/3, right? But Helen was definitely right in that it did actually make it less than 1. A third is less than 1, right? So we can all agree there. Okay, so again, what the negative exponent is doing is it flips the base over. Okay, all right, what is any number to the power of 0? If I gave you x to the 0, it doesn't matter what x is. What will this always be? This is one of our properties. Abby?
Would it be 1?
Yes, any number to the 0 power is going to equal 1. The only exception, which we're not going to deal with in this class, is 0 to the 0. 0 to the 0 we define as being 1, but it's not necessarily 1, and that's something that we'll I'm sure talk about in a future math class. But for our purposes, we're just going to be dealing with bases that aren't 0 raised to the 0. So any number other than 0 raised to the 0 power will always give you back 1. Okay? All right. So let's jump into an example where we actually deal with dealing with reducing exponents and seeing them in action, with division or multiplication or whatnot, right? So let's say we have the following example. We have 3 to the 4th times x to the negative 2nd power times y to the 5th power. That's not a 5. That's a 5. Okay, so y to the 5th power, and now we have in the denominator 3 squared x to the negative 3rd and y squared. And I say I want you to simplify this. Okay, so the first thing that we saw is it can be really daunting to look at this as it currently is, right? There's a lot going on. There's multiple bases, multiple exponents. Some are positive, some are negative, right? So it really helps to do a little bit of matching and see, okay, just pick one base at a time and do, that particular fraction. So the way I'm going to handle this is I'm going to split this up kind of in columns, right? So we see here that we have a base of 3 over a base of 3, right? So we're going to do that one first. Then we're going to handle the x's. And then finally, we'll handle the y's, right? So what I'm going to do over here is, again, just off in my little corner, I'm just going to write 3/4 over 3 to the 4th over 3 squared. So if I have the same base and division is involved, what is happening to my exponents? Should the number get bigger or the number get smaller? Let's start there. Jacqueline?
Smaller?
Smaller, right? We're seeing that it's being divided by a number that's larger than 1, right? So we would imagine that it's getting smaller, right? And so what then is happening to the exponents? If the number is getting smaller, what should the exponents do? Denny? Okay, exponents should also get smaller. You're definitely right. Vincent, I saw the hand go up. Did you have an idea as far as?
Yeah. Do they subtract?
They subtract, exactly, right? So we keep the base the same, so it's still 3, right? And what we do is we just subtract the denominator from the numerator as far as the exponents are concerned, right? So we see that we have the exponent of 2 in the denominator, so we're going to be subtracting that from the exponent that was in the numerator, in this case of 4, right? So we have 3 to the 4 minus 2. Of course, 4 minus 2 is just 2, right? So this is just ends up with 3 squared, which of course we know is just 3 times 3, also known as 9, right? So we end up, just using our exponent rules, we end up with a nice simple answer there. So we dealt with the base of 3. Now let's deal with the base of x's, right? So we have x to the negative 2 being divided by x to the negative 3. Okay. So Vincent just helped us out, right? He said that what's going to happen when there's division involved, and if it's the same base, is the exponents should subtract, right? So somebody tell me what this should come out to be. We keep x the same, right, because it's the same base. So what should happen in the exponent's place? Any takers? Jacqueline, one more time.
1.
Okay, so we have -2 minus a -3, right? And keep in mind, whenever we have two negatives, they cross out and give us a plus, right? So we have -2 plus 3. And of course, just like Jacqueline said, -2 plus 3 is just 1, so x to the first. And we already know that anything to the first power is just itself, right? So we just end up with an x. And now the last but not least, we have y. So we have y to the 5th being divided by y squared. So just to write this one more time, y to the 5th being divided by y squared. And I'll just breeze through this one. Of course, we keep the base the same. We subtract, so 5 minus 2. This gives us a 3. So we have y cubed, and that would be the end for the y base, right? And now just putting it all together, because of course it was all being multiplied, right? Our final answer then is 9x y to the 3rd. And that's it. That's all we do, right? So the big takeaway here is don't stress yourself out. Take it one base at a time and just remember your exponent rules, right? When bases are being divided, exponents are being subtracted. When bases are being multiplied, exponents are being added. And that's it. Just keep in mind that the bases have to be the same base for you to use your exponent rules. We can't do anything with the 3 versus the x or the 3 versus the y because they're not the same base. But notice how, we broke it up into columns. We dealt with the 3 over 3. We dealt with the y over y. We dealt with the x over x. And that's how we ended up with our solution here, 9x y cubed. Any questions on this? Sorry, Helen, Matt, are those hand raises from before or questions? Okay, got it. Okay, so that's all I had for you guys today. Do you guys have any homework questions for me that you want to go over? Is there anything in particular that you wanted to take a look at? Okay, Denny, which homework question?
Wait, hold on. I'm looking for it. Give me just 1 minute.
Sure.
I want to check the question homework 136, which is y plus 3 and then divided by x minus xy.
Sure. Yep. All right. Give me 1 second to write it down.
Is that correct?
You got it. Okay. And okay, so this is what we have. What we want to do is we want to evaluate this expression, and we have some given information. The given information is that x is equal to 3 and y
equal to 5.
Y's are getting horribly bad today. Y is equal to -5. Okay, so what we can do is you technically have two options. You can either try to combine this first. So we have this, the first fraction, right? And we also see that there is this minus xy, and we can try to combine them together. And that could be good practice to do because it helps you, think in terms of common denominators. And, that's always good to do, especially for this course, right? And just to get you started in the way that you would do that, you would remember that x times y is really xy over 1, right? We know that any entity is itself, but just divided by 1. So now we have two fractions, and now you would just think of common denominators, right? So the common denominator between x and between 1 is, of course, just x. And so all you would have to do is multiply the right-hand fraction by x over x. And this, of course, is one way to do it, right? However, there's a slightly easier way to do it, and the slightly easier way is just directly substituting in, right? So what do we know about x and y? Well, we know their values, right? That was the given information. So what we can do is we can just directly substitute in and then simplify, and that should hopefully work out in our favor, right? So if x is 3 and y is -5, let's just plug those in. So we have -5 plus 3 all over 3, and this is minus 3 times -5. And again, remember, we're no longer using x's to denote multiplication. Notice how right here, we're using parentheses to denote multiplication. So please make sure you're getting in that habit. Okay, so just doing this, -5 plus 3, well, that should end up with -2 in the top, or just -2/3. This is minus 3 times a -5. So what we see here is we have 1 negative, 2 negatives. We know multiplication, when you multiply 2 negative numbers together, should give you a positive. So this should really end up being a plus. Okay, so we have -2/3 plus, and then 3 times 5 is, of course, just 15. And here's where you can still get your practice with common denominators, right? So 15 is the same thing as 15 over 1. We want common denominators. Again, common denominator between 1 and 3, of course, is just going to be 3. So we're going to multiply this right-hand fraction by 3 over 3 because we want a 3 in the denominator, right? So we make -2/3, no alterations to it. It's still just -2/3. And on the right-hand fraction, well, this should become 3 in the denominator, and then 3 times 15, which is 45. And now, last but not least, we can just combine these fractions together because they have common denominators now. So we know this should end up with a 3 in the bottom, and it's -2 plus 45, or another way of saying it is 45 minus 2, and you end up with 43, or positive 43/3. And this is your final solution. Any questions?
Thank you. I do not know how did I get 37 over 3, but thank you.
Sure, no problem. Okay, any other homework questions you all want to take a look at? Okay, so before I let you guys go, I do just want to give you this disclaimer. Not all of these homeworks are going to be this straightforward. With the early chapters, again, we're still in the introductory material. It's going to be a little bit straightforward, or some of you may remember this from prior math classes. It's going to start to ramp up. So please keep that in mind for the level of effort that you're putting into the homeworks, because you might require more and more time as the semester goes on. Okay, but that's all I have for you. I'm going to end the recording here. For my new people, if you guys have just enrolled in this class, if you could just stick around for a couple minutes so I can talk to you. Otherwise, everybody else, enjoy the rest of your day, and I will see you on Wednesday.